we distribute the data utilized in each drive in a rotational fashion. It allows us to have a naturally load balancing striping approach. We allow for sparing capacity to be interleaved inside of our distribution. This sparing capacity being distributed evenly across each spindle allows for a very predictable utilization of capacity. And since we build in 20% spare capacity in each drive, right? We have 20% more drives participating for the same capacity as everybody else. Make sense? Yeah. Now we distribute that data evenly that we refer to as rags. This is our data distribution algorithm that we then use to carve sheets and data chunks out to create user volumes. And it rotates across all these in an even fashion such that in a granular fashion enough such that when you have I/O going in this user volume, they get distributed across all, so you get even distributions. That's great for every drive being able to contribute evenly to that user I/O capability, right? So even load distribution, if you will. What we do uniquely is that we have dual redundant controllers that communicate over a low latency, high bandwidth bus. This is a hardware distinction that we build into our hardware that allows us to have a shared memory map between the two controllers, such that whatever I/O this controller sees can also be seen here because we write them evenly in both memory maps. It also allows us to have ability for both controllers to talk to the same disks. This is a traditional dual redundant architecture. The problem is many or all architectures out there ask the drive to do their I/O independently of each other, which means since the drive has only one read fork and he has to figure out which I/O to go, you get contention between where physically on the drive has to get its I/O from independently from between these two. By having a shared seek management software between these two, we create one coordinated read and I/O stream to avoid contention between the two competing I/O streams, right? So this allows for a much more ordered seek I/O stream for the drive to perform better. So we get a lot of free I/O because, well, it's ordered in a way that is more well done for the drive. But that's all the drive I/O that we have when we actually do backend I/O. We also have so these are DRAM memory backup cache. So all I/O that comes into from the host goes into cache. Since it's safe in cache, we can actually decouple the order and how the I/O looks from the front end to the back end. We can reorder, we can resize, and we can do different things to the I/O in memory before we ask the drive to do it. And by doing that, we can also optimize the shape of the I/O in a way that allows the drive to perform better. Okay? So caching algorithms are hugely important to get the most performance out of the drives. Seek managers and how you manage what the I/O in what order you get is very important to do right to get better performance out of it. Mechanical fixation of the drive itself to eliminate environmental excursions for the drive to performance peak has a huge impact on it. The fact that we can actually get more spindles contributing to the same capacity, and we use this 20% of over-provisioning, just like the SSD guys do today, to not only get reliability extension, but we also get performance extensions. Make sense? Does that make sense? Yeah. There's a lot of different things that comes together to create it, but a lot of it has to do with software, and a lot of it has to do with how we distribute data across the drives in a very evenly load balancing fashion, right? So the end result becomes up to 400 IOs out of a 10,000 RPM spindle, right? So 400 IOs out of a 10,000 RPM spindle. This is huge. So if you look at it, our competition usually gets about 120 to 150, maybe, out of a 10,000 RPM spindle. So what they do is that they use a 15,000 RPM spindle instead. So they spin the disk faster, and they make the platter smaller, and then you have the seek optimized. So the performance optimized hard drives, right, has a lot less capacity and uses a lot more energy. So a 15K RPM and you get maybe 160 to 180 IOPS out of that one. So we get more than twice performance out of a slower drive with more capacity, using less energy in a higher dense footprint. So in essence, what this allows us to do is to use this drive and outperform the fast drives with more capacity, less energy, higher density, lower cost, more performance, in longer service life.